Hi everyone, welcome to lecture 3 of Topological Correlators of Supersymmetric Young-Mills and Four-Manifold Invariant. Thank you very much for giving this wonderful lecture series. Professor Manschot, could you please take over the lecture?
Thank you, Jesse, and welcome everyone to this third lecture of the lecture series. Maybe just to start with a quick question, if there are any questions or comments from previous lectures I can elaborate on. Otherwise, I'll just quickly review a little bit what we saw in the last lecture. So we went over the supersymmetric Young-Mills theory and the solution on the Coulomb branch, where the Gates group is spontaneously broken from SU2 to U1, making the theory, in a sense, much more manageable, working with an abelian Gates group. We then, in the last lecture, considered the topologically twist of the Gates theory, and that we can consider the so-called cohomology of the states. The topologically twisted theory has a scalar supercharge, whereas the original theory had spinorial supercharges. The scalar supercharge squares to 0, and we can consider cohomology just like we have, say, the Ram cohomology for D squared is 0. And the fields which lie in the cohomology, this third class of the fields, we can demonstrate that their correlation functions are then independent of the metric, whereas they are depending on smooth structures, because that's what one needs to introduce fields and differential equations in the theory. And we saw a beautiful lecture last week by Clifford Taubes on smooth structures and Four-Manifolds. We've seen a few examples of such operators in the Q cohomology. One is the simple point observable, the trace of pi squared, the scalar of the vector multiplet, which was also if you take the WEF, the order parameter on the Coulomb branch. Another operator is this surface operator, which depends on a homology class X, a two-cycle in our four-manifold capital X. Sorry, I'm using small x, capital X. It's a bit important to distinguish them here. Small x is a two-cycle in the four-dimensional cohomology in the four-manifold. And because it's a topological theory, it doesn't depend on the precise details of this cycle. It only depends on the homology class. And then one of the main results is that we can form correlation functions of these Q-closed observables. And on the right-hand side, if we evaluate them, we find fractional numbers which can be matched with Donaldson invariants in differential geometry, which are defined as certain intersection numbers of differential forms on the moduli space of instantons. So the precise instanton moduli space is then determined by the power of U and I in the correlation function, such that these differential forms precisely span the full dimension of the moduli space of instantons. This equation here. Okay. Maybe at this point, are there further questions? No. So in this lecture and the next, I would like to expand on this use of the low energy effective field theory to evaluate the path integrals and how this matches then with invariance of these of the moduli spaces of instantons and moduli spaces of monopoles. We started this a bit last lecture. We discussed that the path integral on the Coulomb branch takes the following form. So this is a correlation function for some observable O, which can itself be a product of other observables. We get this contribution capital phi of O from the contribution of the interior of the Coulomb branch. And then there are singular points on the Coulomb branch where we receive the Seiberg-Witten contributions. You could, in fact, also think of these as contributions from the Higgs branch or quantum Higgs branch. And there's an important result that is the contribution from the Coulomb branch is actually only non-vanishing for four manifolds with B2 plus is smaller or equal 1, which seems a little bit a limiting effect or result. But as I will explain, actually, we can use it to still using the topological invariants, obtain result for general B2 plus from the structure of this from the structure of the Coulomb branch integral. And we discussed that for B2 plus is equal to 1, that will be one of our main interests. The infinite dimensional path integral reduces to a finite dimensional integrals over zero modes or just constant modes of the field, phi, for example. How this is, this can be demonstrated as follows, that we kind of decompose our fields, in this case, this component A with coordinate z, then on the four manifold as a constant mode plus plus variations around this constant mode, and then with arguments based on Q of t, and one can show that these terms with the non-zero modes are irrelevant if we scale the metric to very large metrics. If we multiply the metric g mu nu by a constant factor t squared and let t go to infinity. Okay. Any questions here? Okay, so let me start here with lecture number 3. And expand in a bit more detail how this looks like. So after restricting to zero modes, we get the following integral. We get the sum over the U1 fluxes. The U1 we had an unbroken U1 gauge group, was unbroken from the SU2. We get a discrete sum over these U1 fluxes, and then we get an integral, which is really now a finite dimensional over the parameters A and A bar. Remember, we had classically that on the Coulomb branch we could bring phi to this form, where the diagonal components were parameterized by A and minus A. Then we have an integral over an auxiliary field, dd. This is one of the auxiliary fields of the vector multiplet. And we have these twisted fermions, which became differential forms, differential form eta and a differential form chi, which we also integrate over. So eta here stands for the zero form, and then chi is a self-dual 2 form. A priori, we can also have the 1 forms, but since we consider manifolds where B2 plus is where B1 is equal to 0, for manifolds with B1 is equal to 0, there are no zero modes for the psi, the functions psi, which were psi sub mu, which were the twisted spinors from the vector multiplet. Okay, so this is what the path integral measure reduces to, just a finite dimensional integral. And then we come to the integrand. There are, first in the measure, we get 2 contributions from topological couplings, which depend on the point on the Coulomb branch U. This is this is a function A of U, exponentiated to the Euler number of the Four-Manifold X, and another coupling B of U, which is then exponentiated by the signature of the manifold X. Remember, signature was B2 plus minus B2 minus of the Four-Manifold. Okay. I will say a little bit more about these. Then we have just the exponentiated action, an Euclidean signature, and then we have, of course, the observable O. Okay. Now this A, we can be more precise about it. A is some numerical constant alpha times du dA to the power 1/2. So it's also completely determined by the Seiberg-Witten solution to all orders. And B is given by numerical constant beta, and then the discriminant of the elliptic curve delta to the power 1/8. So both are determined by the Seiberg-Witten solution. And in fact, to evaluate the integral, we do need the Seiberg-Witten solution in order to get an all order answer. So it's important to have these non-perturbative solutions. Okay, and furthermore, this Lagrangian L0 is the zero mode Lagrangian. So in fact, we can ignore the terms with most terms with derivatives, so it becomes a very simple integral. And we have in fact L0 is a term with the U1 fluxes decomposed, projected to the positive and definite, negative definite part of the middle cohomology. Tau bar F plus with F plus tau F minus X F minus minus Y divided by 8 pi d wedge star d. Actually, d is self-dual, so you could, if you want, write d wedge d, and y is the imaginary part of tau. And then a term with the fermionic zero modes d tau bar over d a bar eta chi wedge F plus d. Okay. Now note that this Lagrangian does depend on the metric by this projection of the field strength F to F plus and F minus. Even though by the general arguments we are expecting a topological result for the correlation functions. I will comment on that later. It turns out that actually for these manifolds with B2 plus S1, correlation functions will not be quite topological, but will have a walk crossing dependence. Maybe to comment on these field strength Fs, they are related to the SU2 field strength as follows. F, the SU2 field strength we started with, then decompose as F over 2, 0, 0, minus F over 2. Okay, any questions so far? Okay, so we sum over these we sum over the U1 fluxes, the gates imposing the modulo the gates transformations. Therefore, we are just summing over the cohomology lattice, and we'll use this parameter L to denote these fluxes. So it's L over, use the normalization 1 over 4 pi times the class of the field strength in the cohomology. And this is an element then in the half integral lattice. Remember, L was identified with h2x over the integers z, modulo torsion to be precise, but if we work with a simply connected manifold, there is no torsion. So lattice L is just shorthand for the middle dimensional cohomology. Normally the class 1 over 2 pi of the times f gives us an integral class. We use here normalization with 1 over 4 pi, such that this mu is then lying in the half integral lattice. Is a choice in the half integral lattice. And mu, in fact, is 1/2 times the second Stiefel-Whitney class of the principal bundle. So if mu is equal to 0, then we can lift to an SU2 bundle formally. We can lift this S in a sense formally as the SO3 bundle to an SU2 bundle. I should, maybe to make it precise, write SO3 here to allow for non-trivial second Stiefel-Whitney classes. If mu is 0, SO3 bundle can be lifted to an SU2 bundle. And if mu is not equal to 0, modulo the lattice L, then if mu is not equal modulo L, then the bundle cannot be lifted to an SU2. SU2 bundle. Sorry, it's a bit small. Okay, but we can still lift it to a U2 bundle, but not to the SU2 bundle. Okay, are there any questions on this? It might be a little technical. Okay, and then we derive a full sum over fluxes, which take the following form. So maybe I should first explain a little bit more. So we have these field strengths projected to the positive and negative definite sublattice. In this case, B2 plus is 1. We have a unique self-dual direction. B2 plus is 1, we have a unique self-dual direction we denote by J. It's you can also say this is the Kähler form. And so we can project an L in in the lattice L as follows, just by taking the inner product on the middle cohomology, B L comma J, divided by the norm of J times J. This gives us L plus. And then L minus is equal to L minus L plus. Okay, then we can form this sum over fluxes. Psi mu J tau bar, 1 over the square root of y, imaginary part of the coupling. We get a sum over all the fluxes, and then we get this inner product. So this, I should stress that this B is completely different from this B. This B here was the pairing on the middle dimensional cohomology. This B is the integral over x of this of the arguments. Hope this is clear from the context which one is what I'm using here. So this symmetric pairing, you get B L comma J. Then there is a tricky sign. I will comment on it. -1 to the B L comma K times Q to the minus L minus squared over 2 times Q to the Q bar to L plus squared over 2. Sorry, I use here lower script, so maybe let me fix this. Here we have this is L plus, L minus, L plus. Okay. Any questions here? Okay, this sign -1 B L comma K. This is a sign which is quite important if we do duality transformations. This capital K is an integral lift of W2 of x to L. So we can, for short, we can just identify it with W2 of x modulo to L. And it is a result. It is a result from integrating out the massive modes. It's a remnant of integrating out remnant mode. Remnant of integrating. Out fermionic. Massive modes. It's discussed in the paper by Witten from 95 on S-duality and abelian gauge theory. Okay. Any questions so far? Okay. So let me just summarize. We have this function, sum over fluxes, indicated by psi mu. Mu is this congruence class. It's a finite number of elements because we sum over the full lattice L shifted by this congruence class. We have these different factored one insertion of B L comma J multiplying the exponentials, and a sign which we saw when I introduced these Jacobi theta series. I think the theta 4 also has a sign. So this is a bit similar to that. And it's important to note that it is depending on this period point, or the self-dual direction in the cohomology, or the Kähler form, if you want, by this projections to the positive and negative sublattices. Okay, to highlight this dependence, I will also give phi the superscript j, and also the subscript mu, to indicate the dependence on these congruence class. Yeah. Okay, and of course we have the observable O we want to calculate. And now I was when I was discussing the Seiberg-Witten solution for the pure theory, I discussed that we get this that the parameter U is invariant under the duality group of the theory, which is gamma 0, 4. And therefore we can act with modular transformations on the effective coupling tau. And we describe these fundamental domains. So for all these reasons, it's actually useful to change variables from A and A bar to tau and tau bar, since the domain for tau and tau bar is in a sense better understood than the domain for A and A bar a priori. So that's what we will do. Maybe another comment at this point here is that if you're considering these theories in flat space, then typically A and A bar, we keep them fixed. They are like boundary conditions in the non-compact flat space. But since we are doing a path integral here on a compact space-time, we integrate over all these modes. So the final result here on the left-hand side will not depend on A or A bar, because we do the full integral over these scalar fields. There's no boundary, so we integrate over the full space of over the full field space. So we change variables to tau and tau bar. And then the integration domain for tau and tau bar is the upper half plane H, not gamma not 4. Okay. And I should say actually that we integrated out the auxiliary D field and eta and chi. So eta and integral over eta and chi, they bring down the factor of f plus, and that's precisely this factor which multiplies which enters here in the sum over fluxes. So I've integrated out the D field, which gives us this 1 over y, and the sum over and then the sum over these fermions, it brings down this f plus. Then we see that we have the d tau bar, the A bar comes down, but it's already showing that there's a natural change of variables to tau bar. And we have to then put in the Jacobian for tau, so that comes in the measure nu of tau. So we have nu of tau now is our new measure, which includes this Jacobian dA d tau, and then these topological couplings, A to the Euler number of the four-manifold, and B to the power the signature of the four-manifold. And then we get this sum of fluxes psi mu j tau bar. Okay, are there any questions here? Okay, and so now, in order to see that this integral is well defined, we need to show that this is actually the whole integral is invariant under transformations of gamma naught 4. It means that you can choose any fundamental domain for gamma naught 4 in the upper half space H would do. It is independent of the choice of the fundamental domain. And it's an independent, it's a non-trivial check to demonstrate that this is in fact the case. There is gamma 0 for invariant, the duality group of the theory or congruence subgroup, if you want. Okay, this is papers on the subject, usually done in great detail. For example, the paper by Moore and Witten, 1997, other papers, more recent papers. Okay. Any questions? Okay, and so then the question is how to evaluate this. I should also not forget the observable here. For the surface observable, actually, the surface observable, you need to include it in psi because it depends on the flux F. I can maybe briefly go back to the surface observable to see this explicitly. We see here the surface observable depends on the 2D the SU2 gauge field F. If you go to the low energy effective version of this surface observable, it will depend on the U1 field strength, so therefore you should. One cannot factor it out of the sum over fluxes, but it will be you'll get a more complicated kernel in the sum over fluxes. But let me not go into those details. So we can assume that O is trace phi squared or a power of trace phi squared for now. Okay. Anyway, in both cases, there has been made good progress in recent years on the evaluation using mock modular forms, which do appear quite widely in this context. Progress. Evaluation. Mock modular forms. And to maybe explain this in some detail, let us consider a specific example. We can consider the example of the complex projective plane. So we can take X is CP2. Complex projective plane. And so the topological numbers of this four-manifold are that P2, second Betti number, is equal to the P2 plus in this case, so it is equal to 1. So we just have a one-dimensional cohomology lattice, and it's positive definite. And it has B1 is equal to 0. And so, yeah, we take as a sample the complex projective plane, but actually the only thing what is important for us here as input for this integral is that is chi and sigma. So chi is equal to 3 and sigma is equal to 1. And there are actually many four manifolds with these topological numbers. There's also, I think, the fake projective plane that related to the talk Clifford Taubes last week, that there are many smooth structures. Can be many smooth structures on a manifold with given topological numbers. For this, the calculation applies to all the manifolds which have these same topological numbers. Okay, then we can evaluate this psi mu. Psi mu in this sense actually in this case becomes doesn't really depend on this Kähler form J because it's just it's one dimensional. So it is, since P2 plus P2 is one dimensional, there's really no freedom to choose J. And then what one finds is that this is actually 0 when mu is equal to 0, simply because of this factor here that all the terms cancel in this combination. But if mu is equal to a half, or a half times the hyperplane class is maybe a better way to say it, then we get a non-vanishing answer. It is minus I divided by 2 square root of 2y times the complex conjugate of the eta function to the power 3. Okay, is it useful to recall the definition of eta, or is everyone comfortable with that? Okay, well, maybe just quickly. Eta of tau is equal to q to the 1 over 24 product 1 to infinity 1 minus q to the and then we have a measure. This measure nu of tau. We can evaluate all these different terms completely concretely, and one finds that nu of tau is minus I over 8 times the Jacobi theta series theta 4 tau to the power 12 divided by a power of the delegate eta function eta tau to the 9. And just to recall, theta 4 of tau was the sum over integers minus 1 to the n q to the n squared over 2. Okay. Okay, so we have a very well-defined integral to carry out now. We have this this measure factor, and then we have psi. You can 1 over y has weight 1/2, 1/2. 1 over the square root of y has weight 1/2, 1/2. So one get an anti-holomorphic weight then with eta tau cubed weight 2. And we see here that here we also have weight 3/2. So combining this with the weight 1/2 from this term, we get also weight 2, which cancels precisely the weight of the measure d tau, which d tau bar. So one sees at least at the level of the weights that we get the right an invariant function. Then you can check also the periodicity setting tau to tau plus 4 to show that it indeed is invariant under these the generators of gamma 0 4. Okay, now we would like to integrate this using Stokes theorems, using mock modular forms. I won't give a full account of mock modular forms here. That would leave us a little bit too far astray. But just I will complete this example using that technique. and then hopefully you get enough of an idea how to carry out these type of integrals. Integrate using Stokes theorem. Multi-modular forms. This goes back to my work with George Korpas, 2017, and a paper with Greg Moore, Yuri Nidayev, George Korpas, and myself, 2019. There's also earlier work by Malman J and Ono. And in hindsight, you can also recognize mock modular forms in the paper by Moore and Witten, even though the terminology was not developed at that time. So an example of a mock modular form is the following. I will just write it down explicitly. You have a function f of tau, but it is now a bit more complicated than the ones we have seen. It's 1 divided by the theta 4, and then a sum over integers. Minus 1 to the n, q to the n squared over 2, minus 1 over 8, divided by 1 minus q with the exponent n minus a half. The one sees it's a little bit more involved. It's in fact a ratio 1 over theta 4, and then we get this sum over integers. It's not just q to the n squared, but we have a denominator, non-trivial denominator, also depending on q. We can make an expansion 2 times q to the 3 over 8. Easy enough to put this on Mathematica and make an expansion. First terms are 1 plus 3, q to the 1/2 plus 7 times q plus further terms. I didn't specify it in my notes here, but I believe this function or related functions, they also show up in the phenomena of moonshine, where these coefficients of the Q series count irreducible representations of finite groups. Now the special property of this function is that it does not transform as a modular form itself, which is pretty much because of this kind of more involved summand. But yet it is it transforms in a sense almost as a modular form, and we can easily modify f by writing down its completion. I should say this is the mock modular form. And now we have an associated so-called completion, which we standard to denote by a hat, and which depends on tau as well as tau bar. F tau, it's the function f. And now we add another term to it, which is an integral, so-called Eichler integral. It starts in the positive, in the upper half plane. It's minus tau bar. So tau bar, of course, element of the lower half plane, but now we are back in the upper half plane, multiplying it by minus 1. Then we integrate up to I infinity theta of w cubed, and we divide by minus I times tau plus w dw. This transforms as a, I believe, weight 1/2 modular form. Right. 1/2 modulo formed 4, 0, 4. Okay. Any questions so far? Okay. So yeah, this now it's also hopefully becomes clear why I discuss precisely this function. This non-holomorphic term of the completion involves this power of eta, which is precisely the same as we had that the function psi evaluated to this psi power of the eta function. So we up to and then combined with this denominator, we find that the tau bar derivative of f hat precisely combines to something proportional to the function psi mu. Okay. Any questions so far? Okay. Then we can evaluate this phi mu for this generator of correlation functions, e to the 2pu. P is the kind of the generating variable, u is the field. Then he evaluates to the limit of y equal to infinity. We'll expand on this a little more. So we have this fundamental domain for gamma 0, 4. It's not gamma 0, 4. This. Okay, so we aim to apply. We are not going to use Stokes' theorem. Maybe I can indeed add this. So we have this integral d tau, which is d tau bar, h mod gamma 0, 4, mu of tau. Mu of tau is holomorphic, so I can just put d tau bar acting on mu of tau f tau bar. So now using Stokes, we're going to go to the boundaries of this fundamental domain. To do that, we will compactify the domain by cutting off these asymptotic regions. So say we cut it off here, here, and here. Now these sides were identified really. This side with here, this side with there. So those are identified. So that's why if we go to the boundary, we are only left with these boundaries which cut off the asymptotic regions. And that I will denote by y. So this is at im tau is equal to y. And we can take similar parameters here in the local tau parameter. And then we evaluate and we take the limit y going to infinity. So we take the limit y to infinity of the boundary of this domain. Which is cut off at the point parameterized by y. This is the shorthand notation. Then we just have this integral over d tau, nu of tau, f hat of tau and tau bar. And sorry, I tend to forget the observable e to the 2pu. E to the 2pu. So yeah, we can just in terms of real parameters, tau is equal to x plus I times y. Use it now here. There's no surface observable in the picture here, so I can use x for the real part of tau. Then this integral is just integrating the real part of tau from -1/2 to 3/2, and we just pick up the constant term due to that reason. Similarly, at these strong coupling cusps, we can go to a dual parameter sending tau to -1/tau. Then we get a dual tau parameter here at the cusp, which we again can integrate in that case from -1/2 to 1/2, and here also from -1/2 to 1/2 for the local parameter 2 -1/tau. So this one, they can plot that here, that this parameter here is tau 0 is -1/tau, and here we have a tau tau is equal to 2 -1/tau2. Tau2, it's better to write it the same thing here. But tau is equal to -1/tau0, and then sending tau0 to I infinity. It's the dual weak coupling limit near this strong coupling cusp, and here we have a dual coupling tau2, which becomes weakly coupled if we approach this dione cusp. And in this way, we then find that we get the limit of y going to infinity 4 times mu of tau f hat tau bar e to the 2pu q0. And then there are these, so this is from the weak coupling cusp. Then there are two extra terms, which I will add schematically, tau to -1/tau, constant term q0, plus the integrand with tau 2 tau -1/tau q0. And if we take this limit, sending tau, this y to infinity, actually this non-holomorphic part of f hat will go to 0. It's a subleading part of f hat. So we're just left with 4 times mu tau f tau e to the 2pu. And one can demonstrate that these terms then have no constant terms, so there are no further terms. And one can check that this then reproduces a much older result derived in the algebraic geometry by Goethe and Ellingsworth, where they really needed the machinery of complex algebraic manifolds to evaluate the Donaldson invariants. I think this went back to maybe 95 or something. So these are the results for Donaldson invariants. Okay, so maybe this is a good point to pause and see if there are any questions. Okay, are there any questions about the first bit? Maybe a bit technical, or many different techniques coming together. Okay. Okay, so we discussed now just one example, which is always kind of the first case to consider in this type of calculation, this manifold of the complex projective plane, since the cohomology lattice is just one dimensional. Let me comment a little bit on if you have a more complicated manifolds. And if you have a manifold with B2, first we consider a four-manifold X with B2 X larger than 1, and still B2 plus of X is equal to 1. Then we have a choice of this parameter J, since we have a whole cone of positive definite vectors. Okay, then we can still evaluate correlation functions like this, or integrals like this, very much in the same way as we did here, using this Mock modular form f of tau. But the function f of tau is now replaced by what is known as an indefinite theta series. Tau is replaced by an indefinite theta series. Also, maybe add that this whole subject of Mock modular forms and indefinite theta series goes back to the Indian mathematician Ramanujan, who really had many insights in all these functions about 100 years ago already. It's really impressive. So in these indefinite theta series, they are theta series for an indefinite lattice, such as the ones we are looking at now. We have one positive direction and then B2 minus 1 negative definite directions. One way to get a convergent series is as we were doing in this case of psi, where we simply project them to negative and positive definite subspaces, and we exponentiate with tau and tau bar to get a convergent series. Another way what we can do is that we are just here we are still summing over the full lattice, but alternatively we can also sum over only a subset of the lattice of vectors which are positive definite. And that is what this second technique does of the indefinite theta series. So we have a theta series, theta mu, which now depends on two parameters, J and J prime. Actually, I'll make a couple more comments. Second, we sum over the full lattice, but we include a kernel which has only support on a subset of the lattice. We take the sign of BL, J minus the sign of B L, J prime. And then we multiply with our convention, in this case, minus L squared divided by 2. Okay, so again, our B here is the bilinear form on the middle cohomology. Both J and J prime are positive definite vectors. And so what we can calculate now is actually at first instance, it's not the full partition function, but rather the difference of these partition functions or correlation functions. Then if we take the difference phi mu j e to the 2pu minus phi mu j prime e to the 2pu. Then what you'll find is a similar formula, namely 4 times mu of tau times this indefinite theta series j prime tau 2pu. And then possibly these other terms where we send. Actually, maybe I should write it a little bit better. So tau is equal to minus 1 over tau 0. And then we take the constant. Here we take the constant term q0. And then here we take the constant term in the parameter q for q0. This is q0, 0. And then for the second bit, we take the integrand. We have another strong coupling singularity where we replace in the integrand tau by 2 minus 1 over tau 2. And then we consider the constant term with respect to this Q series. Okay. Okay, any questions so far? So if these two are not equal to, if the difference of these two is not equal to 0, then we have the phenomenon of Bohr crossing. So if this is not equal to 0, then we have phenomena of Bohr crossing. So we find for these type of manifolds that that there are jumps where this difference, you can have points where this difference is equal to 0, but then if you change j versus j prime, then at some point this might become non-zero, and then you get a non-vanishing result for the right-hand side here. And this happens across these codimension 1 loci in the space of J. And so that we have a function which is locally constant, phi mu J is locally constant as function of J, but for these manifolds with P2 plus is 1, there can be jumps across wall of marginal stability. Okay. Okay, but there are jumps for codimension 1 loci in the domain. J, and that's the phenomena of Wall crossing. It is special for these manifolds of B2 pluses is one, that there can be this kind of discrete metric dependence. That's only for this theory. We'll see later that there can even be a continuous metric dependence for some other theories. Okay, any questions? Okay, now another comment is that here we see that we consider the right-hand side. We can take the difference of these contributions of the columbrans. On the right-hand side, we get three contributions associated to these to the three cusps. Can be Wall crossing then due to the cusp at weak coupling and these strong coupling cusps. Now, but for physical reasons, there can only be Wall crossing really from the boundary of field space. And these interior points, we saw them in the U-plane. They are not really the boundary of field space. They're in the interior. So for that reason, one expects that if you go back to the general formula for the path integral here, the full correlation function decomposed into a contribution from the U-plane plus a contribution from the singular points, the Seiberg-Witten contribution, that there is a complementary Wall crossing from the Seiberg-Witten invariants, which is going to cancel the Wall crossing from the U-plane for the strong coupling cusps. So just to spell this out in some detail, we have Wall crossing can only arise from the boundary of field space. And so that the Wall crossing of phi mu j due to strong coupling to the strong coupling cusps is cancelled by is cancelled by the contribution from the Seiberg-Witten by the Seiberg-Witten contributions OSW. So this gives us now an interesting interplay. What I was hinting at before, that if you know how the U-plane contribution is going to change, then this since it has to be cancelled, this kind of greatly specifies this how the Seiberg-Witten contributions, the form of the Seiberg-Witten contributions. The Seiberg-Witten contributions are determined by the so-called Seiberg-Witten invariant. So recall for the Seiberg-Witten invariant, I think we haven't really seen them in the lecture so far, but this is an invariant which considers which is an invariant for the monopole modular space. It's an invariant for the monopole or Seiberg-Witten equations. Paper by written from 1994 on four manifolds and monopoles. those equations look a bit like f plus a bilinear term in terms of the spinors, m bar, must be equal to 0. And then there's the Dirac equation acting on n is equal to 0. And this is the equation. This is we were discussing that there's a monopole or dion becoming massless at the singular points. There's not just a monopole or dion by itself. It comes as a supersymmetric multiplet. It happens to be a hyper multiplet. And as I will discuss soon, actually, the twisted the twisted scalars of the hypermultiplet, they become these spinorial fields. So this is how you can see that then at the singular point in the U-plane, we get it's governed by the so-called Seiberg-Witten invariant, which is the counting invariant for the moduli space of these monopole equations, and they in a sense, they are quite easier to work with since they are just for an abelian. In this case, an abelian field strength F rather than an SU2 non-abelian Yang-Mills field strength. And one can show that these for B2 plus is 1 also undergo wall crossing. For Seiberg-Witten invariants, I will use the standard notation for these invariants is by just writing SW, and then we have a spin C structure C, or this is a two-dimensional cohomology class, which is specifying the line bundle, specifying the field strength, the first germ class pretty much of the bundle associated to this field strength. And then we have the scalar form J minus the Seiberg-Witten invariant evaluated for a different scalar form. And this is then equal to just a sign, minus times -1 to the NC, where NC is a specific dimension. Yeah. It's not necessary to write it out here. And then the Seiberg-Witten contributions take the following form. So for the full partition function Z, Seiberg-Witten, it's a sum over these two singularities 1 and 2. We get the sum over the Seiberg-Witten, so-called Seiberg-Witten basic classes C, SW, C, J. And then we have a set of so-called universal functions, A, J to the power chi, B, J to the power sigma, E, J to the power C squared, F. These are depending on mu. There can be a few others. These latter ones, they are called universal functions. They are independent of the Four-Manifold. All the dependence on the Four-Manifold X is just in these Euler numbers, chi, sigma, and the Seiberg-Witten invariants. The Seiberg-Witten invariants, in fact, are the invariants which are then dependent or can be dependent on the smooth structure and can in that way distinguish among smooth structures of a Four-Manifold. But these functions are independent of the Four-Manifold. So once you know them for once you derive them for one four-manifold, you can universally apply them for other four-manifolds. Now recall that on the left-hand side, we had this features the generating function of Donaldson invariants. So we see here this correspondence that the Donaldson invariants are expressed on the right-hand side by the Seiberg-Witten invariants, then multiplied by certain universal functions, but their full kind of data dependence on the fundamental dependence on the four manifolds is contained in the Seiberg-Witten invariant, since the chi and sigma here are very basic in invariance. So in this way, it relates to the Kronheimer Morocca structure theorem. And then with this technique of walk crossing, we can derive these universal functions from the U-plane integral. So even though this formula will be more generally valid for B2 plus, not just equal to 1, we can determine these functions A, B, E, F for manifolds with B2 plus is 1. And then since they are universal functions, we know the partition functions also for manifolds with B2 plus larger than 1, where the U-plane does not contribute to the path integral. We can. AJ, etc. Okay. Any questions so far? Okay. So this in the sense, so far today I discussed just the basic topological theory, where we have the topologically twisted vector multiplet with just bosonic fields, complex scalar field phi, and vector potential A mu. I would like to also introduce theories with hypermultiplets and topologically twisted hypermultiplets, then to connect to the topological theories. So recall, as we were discussing in the first lecture, that we have originally untwisted theory. We have these scalars Q and Q tilde in the untwisted theory. Sorry for the abuse of notation. These are, of course, now not the generating. These are not related to the effective Kaplan constant, but these are just denoting the scalar fields in the hypermultiplet. And these formed two doublets under SU2R. Um, 1, 1, 2. This is Q tilde dagger. Gave us the representation 1, 1, 2. They're scalar fields, so they are singlets under SU2 plus, SU2 minus, and two-dimensional under SU2R. And we had the representation formed by minus Q tilde, Q dagger, gave us the representation, another representation, 1, 1, 2. And now if we do a Donaldson-Witten twist, then we were instructed to take the diagonal representation of SU2 plus and SU2R and form a new Lorentz group with an SU2 prime. This is the diagonal group of SU2 plus and SU2R. So we twist. And now for the SU2 plus SU2 minus times SU2 plus prime, we get the representation 1, 2. This is SU2 minus times SU2 plus prime. And similarly, this is completely analogous for the bottom one. We get 1, 2. And so, crucially, these are spinors. Okay. So whereas in the case of the vector multiplet, nicely the spinors were replaced by differential forms, and then we could formulate the twisted vector multiplet on any four-manifold. Now, if we include hypermultiplets, then we see that our original scalars of the theory they have turned into spinors, which is complicating the picture, since not all four-manifolds are spin, and you would like to formulate these on any manifold. We can go around this as follows, by recalling that we have for each hypermultiplet we have a flavor line bundle L. It's hypermultiplet with a flavor line bundle L. This is we have a U1 flavor symmetry acting on the hypermultiplet. If you have several hypermultiplets, we can consider larger non-abelian groups. But at least we have this flavor line bundle. We can choose to be this line bundle is non-trivial. It's not just a flat bundle, but we can allow it to have some curvature. And in this way, we can couple the twisted field to a spin C structure such that it is well defined on any four-manifold. We can choose C1 of L as we call it CUV, as a UV spin C structure. I should say actually these spinor fields, we denote them by M alpha dot. I'll have it here. This is M alpha dot, and then this is M bar alpha dot. And yeah, this depends a bit on which representation we have for the hypermultiplet under the case group. This is in fact for the adjoint representation. If the hypermultiplet is in adjoint rep of the case group. Okay, any questions? Okay, I think already the lecture last week I also mentioned there's a canonical spin C structure on an almost complex manifold X. If X is almost complex, there is a canonical spin C structure given by the canonical class. Canonical spin C structure. Is Kx such that the square of CUV is 2 chi plus 3 sigma. And then our S minus times L to the 1/2 is identified as W minus identified with differential forms of degree 0, 1, and S plus times L to the 1/2 is W plus identified with 0, 0 plus lambda 0, 2. So then we are back in the language of differential forms, and we can formulate it on any four-manifold. But we have an infinite set of choices for CUV. We have this whole lattice modulo W2 of X. So this gives us all, in a sense, different twists. And you'll see that we get different correlation functions depending on the choice of CUV. Okay. Any questions so far? So this is the quantization condition if for the adjoint representation, then we can ask about the quantization condition for the fundamental representation. So that couples differently to the gauge group, and as a result, we have there of course that CJ is that C1. Maybe I should also recall here that if we add a hypermultiplet in the adjoint representation, we can only add 1, because if we add more, you would in theory would not be asymptotically free. So I don't have to add an index for the number of hypermultiplets in the adjoint representation. It's if we don't include a finite mass, if the mass vanishes, then it is really n equals 4 super Yang-Mills. With mass, it is known as n equals 2 star, since it's a mass deformation of n equals 4. For the fundamental representation, we can add up to 4, and then we get the following quantization condition, namely that C1 of Lj must be equal to 2 times mu, which this was W2 second Stephen-Whitney class of the principal SU2 bundle of the gauge group, plus W2 of X or Kx modulo 2L. This was derived in that paper with my students Asman refer that myself in 2022. There's also recently a work on deriving these type of conditions for general functions or general theories of class S by Moore, Saxena, and Singh for general class S. Six. Okay, any questions? Okay, so now we saw if we just have the vector multiplet, then the equation of interest, the differential equation of interest was the instanton equation for instantons, f plus is equal to 0. Now, including these hypermultiplets, we get a set of differential equations which are known as the non-abelian monopole equations. So let me just formulate them, assuming that X is a spin, that I can use spinor indices. Then these take the following form. We get Fa plus alpha dot beta dot, where I have the indices of a self-dual field strength. I've translated them to spinorial indices using the Pauli matrices, plus a quadratic term in terms of these twisted of the hypermultiplet scalars. J is 1 to NF, M bar J alpha dot T A MJ beta dot is equal to 0. And the Dirac equation for these spinors, D bar M J alpha dot is equal to 0. These equations go back to the math literature, Pristry, Koch, T. Uren, 1995, soon after the abelian version of this by Witten. There's a paper by Labastida, Mourinho. Also 1995, I think, and Ian Lunes, I think also this time, maybe 1997. And here TA is then in the representation, in the Gates representation of the hypers. Okay. Any questions so far? So this is in a sense, a non-abelian, or this is a version of the instanton equations, but now including these hypermultiplet fields. So if this is 0, you're just back with the instanton equation. But in the case of these hypermultiplets, we get this additional term and the Dirac equations. Okay, now you can denote the moduli space of these solutions. Just want to give it a name, like curly M. MQ, K, CJ, or CUV if we have the adjoint hyper. And we can calculate the dimensions of these moduli spaces. So in the adjoint case, CUV, you'll find that these extra equations and these extra terms, they were then reduced to the following dimension: 3 CUV squared minus 2 chi minus 3 sigma over 4. And we had that CUV, we had to see a quantization condition. I don't have to repeat it. The quantization condition that CUV is a spin C structure that it is equal to W2X modulo 2L. And we see for the canonical spin C structure that the numerator is just 0. And so it's also special from this perspective that the moduli space, this MQ, is actually 0 dimensional. I don't know how much you know about other topologically twisted theories, but if you know about Alpha-Witten theory, it's maybe of interest to mention that the field content of this theory is isomorphic to that of Alpha-Witten theory. Content is isomorphic to Alpha-Witten theory. This is a different twist of Wernicke's Fourier wheels. There we have a real scalar C, a real self-dual two-form B, and then of course the Young-Mills field strength. And my paper from 2021 on the n equals star theory with Greg Moore, we argue that the n equals, that this moduli space for the non-abelian, for the n equals 2 star theory, these non-abelian monopole equations, I should say, the non-abelian monopole equations for that specific spin C structures are a compact deformation of the Alpha-Witten equations, and therefore the partition functions are identical. That is out with the non-abelian monopole equations. Are a compact deformation of the Alpha-Witten equation. I won't go into the details here, but you can find them in the paper from 1994 on the strong coupling test of S-duality. And we therefore argue that the partition functions of the two theories are the same, or correlation functions. Of both theories are the same, at least on these almost complex manifolds. Almost on a four-manifold X with an almost complex structure. Okay, similarly, are there any questions? Maybe similarly then for the fundamental representation, we can also determine this dimension using index formulas. So here we see that the right-hand side still does depend on the instanton number. Takes the following form. It's 2 times 4 minus NF times the instanton number K, plus 1/2 times minus 3 times the Euler number, minus 3 plus NF times the signature sigma, plus a sum over these classes CJ squared. Okay, and you may check that this is in fact an integer if this quantization condition is satisfied. A priori, it might not be clear that this is an integer because of this factor 1/2, but with the quantization condition for these CJs, it will come out as an integer. Okay. Okay, maybe this is a good point to pause for today. Then I'll explain tomorrow how to localize to either instanton and monopole branches of these moduli spaces, and what we and the discussion about the contributions of these various branches. Yeah, thank you for your